It's kind of like you guys sitting during class. You're in your seats. You're wiggling around a little bit, but you're not escaping. You're not sliding all over the classroom. The liquid would be like you guys during a lab where you're still contained in the classroom. You're still connected with each other. You're not escaping into the hallways. And a gas would be like ringing the bell at the end of the day. Everybody goes their own way and makes lots of collisions in the hallway, eventually escapes out the doors, and everybody goes in their own direction. More energy you have, the more movement. Here's another picture. Here's solid ice. You see the nice, neat arrangement that these little water molecules have. Here's liquid water. All the particles are free to kind of bounce around and slide by each other. And here's gas. Notice a lot of space between the gas particles. So particles vibrating in a fixed position in solid. Liquid, they're sliding by each other. Gases colliding randomly and able to escape from the container if the container is open. What state of matter you have depends on how much energy you have. Here's an example of sodium. This is solid sodium. Notice you can cut it with a butter knife. All the particles are there just vibrating back and forth. Here's sodium melted in a liquid state, and now we've got particles sliding by each other. And finally, here's a tube that contains some sodium gas, and the particles are bouncing around, lots of space between them, making lots of random collisions. More motion as we go to the right. So here's a nice animation of the three states of matter. You're going to be asked to draw these guys in the future. If you draw a gas, you draw your container with lots and lots of particles bouncing around. Notice how they collide with each other. We're going to talk about that later in the year. That's gas pressure, particles colliding with each other and with the size of the container. And if you open up the container, they're allowed to escape, and they kind of go their own random direction. And they're moving super fast in there. If you draw liquids in the future, make sure you draw the particles near the bottom of the container. Notice how they're not bouncing around up near the top like the gases were. But these guys are free to slide by each other. They're bouncing around. They have a little bit less motion than gases do, but you're going to see that they have a lot more motion than the solids do. So those are your liquid molecules. And notice again how they're near the bottom of the container. They pour, they flow, and gravity is going to pull them down, and they're going to stay down. They don't take off. They don't escape like the gas particles do. Here's solid particles. If you zoom in on this, you can see that those particles are in motion. They're moving, but they're not moving by each other. They're kind of stuck in one spot, just kind of vibrating. And if you pour it or let them fall out, they all stay together. There's attractive forces there. Rewind that if you want to see that animation again. Alright, so characteristics of solids. These are things we talked about. There are strong forces holding them together. Oops, let me go back. Strong forces holding them together. The particles vibrate around a fixed position, meaning they're stuck in one spot, just like you are stuck in your seat during the school day, but you can kind of wiggle around. The particles are packed closely together. They're usually in some sort of organized pattern, but we'll talk about ones that are not organized. They're dense, meaning they're packed as close as they can to each other. They're incompressible. We can't squish them any closer. They expand a little bit when heated. The room between the particles gets a little bit more when you heat them because they're moving around a little bit more. They have a fixed or definite. Fixed or definite means it's not going to change. The volume is not going to change. It's going to stay the same. And a fixed and definite shape, unless we call them amorphous. We'll talk about this word a little bit later on. But a means without or not, and morph means shape, so it doesn't have a very specific shape. For instance, Play-Doh. Play-Doh is definitely a solid. It's not a liquid or a gas, but it could come in all different shapes. Whereas diamond has a very specific shape that it would come in. Or a pencil has a very specific shape. Characteristics of liquids. They have weaker forces holding the particles together. That's why over time liquids can evaporate, because the particles don't stay together as well as they do in the solid form. Some particles can bing, bing, bing and just kind of escape and go into the atmosphere. Particles in a liquid slide by each other. They're free to flow. They are dense and incompressible. You really can't squish them any further, just like solids. They do expand slightly when heated. This is why we can use mercury or alcohol in a thermometer. If you heat it up, the liquid will expand and move up the thermometer. They have a variable. Variable means change. Indefinite means it's not definite. It's not the same thing all the time. So they have a variable or indefinite shape. Basically, it takes the shape of the container. So if you put it in a Mickey Mouse shaped bowl, it'll take the shape of the Mickey Mouse shaped bowl. If you put it in a long, skinny, graduated cylinder, it'll take the shape of the long, skinny, graduated cylinder. So whatever container it's in, it'll take that shape. The important one here, and this is one a lot of kids get wrong, the volume is fixed. The volume of a liquid will not change. It doesn't matter what container you put it in. If I have 5 milliliters of something, it'll always be 5 milliliters. Kids get this one wrong. For some reason they think the shape changes and they also think the volume changes. That is not the case for liquids. I can pour it from one cup to the next, to the next, to the next. It'll always be the same volume. It just may appear different. And characteristics of gases. These guys have no forces keeping the particles together. It's kind of like the bell ringing at the end of the day. Everybody leaves, everybody does their own thing. They spread out as much as possible. They spread out to fill any volume. The particles are constantly colliding with each other and they move super, super fast. They are compressible. This is why you can fill up a tank and with propane at the beginning of the summer and use it all summer long on your grill or with your grill. They are compressible. We could take all that gas and squish it into one tiny little tank. And this is because there's so much empty space between all the particles. Gases flow. This bullet down here flows. This is important. Remember this one. A lot of kids miss this one also. Gases can flow just like a liquid. And in class you'll see carbon dioxide flowing. Both the volume and the shape are variable or indefinite, meaning they can change. Gases can expand to fill its container, so the volume will depend on the volume of the container. And the shape. It'll take the shape of whatever its container is. This is a picture of gases here. Notice all the collisions. Gas particles are moving super fast. They have a lot more kinetic energy than solids or liquids. They have less mass, if you're talking about a certain sample, because the density is a lot less. But they have a lot more energy. Take a look at this. Oxygen molecules, the oxygen that's zipping around your head right now, about 1,000 miles an hour at room temp. And finally, just a quick little definition here. You've probably heard the term vapor, water vapor. You've heard the term gas, obviously. The terms may be used interchangeably. You may hear vapor meaning gas and gas meaning vapor, but there is a difference. Gas, the word gas is what we use when we talk about substances that are typically in the gaseous phase at room temp. They're typically a gas at room temp. Vapor we use for things that are typically a liquid or a solid at room temp. So gases, they're always gas at room temperature, and vapors, they're usually not a gas at room temp. For instance, water. At room temperature at 22 degrees Celsius, water is water. It's a liquid. So we would use the term vapor when it's in a gaseous state. So we talk about water vapor, we really don't say water gas. We will say oxygen gas because at room temp, oxygen is a gas. It's not a liquid or a solid for that matter. Same thing with carbon dioxide. Carbon dioxide gas because it's usually a liquid, or it's usually a gas at room temp. Mercury is a good example. Mercury is a liquid at room temp, so we call it mercury vapor. Okay, and that's it.